This is lecture 21, and in lecture 21, we're going to talk about the kind of best tests. So we've talked so far about hypothesis testing, and then we've talked about how to construct tests, and the kind of one of the most general ways of constructing tests is using what's called the likelihood ratio test. And now we're going to talk about how do we determine if a test is kind of best, and what does it mean for a test to be the best test in some ways for a certain hypothesis. So that's the main component of this lecture. And the title of our lecture is Most Powerful Test, with gestures at how we're going to define best. And basically we're going to define best as most powerful. So let's start off with a definition. And our definition is of a uniformly most powerful test. And this is often denoted UMP for uniformly most powerful. So we're going to define this uniformly most powerful test kind of generically. We're going to say let's just call it script C be a class of tests. We could even just say a collection of tests. Testing the hypothesis H naught that our unknown parameter theta is in theta naught versus HA, which is that theta is in our alternative hypothesis. So the idea is that if I have this hypothesis, whatever it is, generically we're saying it's some fixed hypothesis, theta is in theta naught or theta is in theta A. There are many different ways I could construct tests. We looked at one of them, which is a likelihood ratio. But the definition of a hypothesis test is basically just the definition of a rejection region for this test. And there are many ways I could form that rejection region. And there may be other procedures I could develop for testing this hypothesis test, or this hypothesis. So we're going to let script C be just a collection of these tests. But they're all testing the same hypothesis. So maybe I construct it one way, and that's when my collection is constructed another way, that's when my collection is constructed another way, and that's my collection. And so I have this whole collection of tests, and I want to define what I mean by the uniformly most powerful test of this collection. So we say that a test with a power function beta star of theta. So for each test in this class, they're going to have some associated power function. And their power function tells us the probability of rejecting. Well, we could just write out what the power is, right? It's the probability that we reject for the particular value of theta. So it's typically viewed as a function of theta, right? And we want to reject, obviously, when the alternative is true, and we don't want to reject when the alternative is false, or the null is true. If we reject when the null is true, that's called a type 1 error. If we reject when the alternative is true, that's called a correct decision. So for any test in my class, it's going to have some power function. If I have a particular test in this class, and it has a power function, let's call it beta star. So I pick a test that has a power function called beta star. A test with this function is called the uniformly most powerful test, or UMP, and I'll say parenthetically for this collection. And we'll talk a little bit about why I'm specifying for a collection. we call this test the uniformly most powerful test, or the UMP, if beta star of theta, the power function for this test, is larger than the power function for any other test. So where beta is another test in my class with a power function beta. So I have a collection of tests. How I came up with these, we don't really specify at this point. They're all testing the same hypothesis. I'm going to say the best test, the uniformly most powerful test, is the test whose power function, generically beta star, is bigger than the power function of any other test. And the power function of any other test, we're saying, is called beta. And we want this to be true for all theta in our alternative hypothesis, right? I don't care if the power function is larger in the null, right? In fact, you want the power function generally to be small when the null is true, because you want the probability of rejecting to be small. But when the alternative is true, we say a test is kind of powerful if it will, with high probability, reject, right? So that's what we mean when we say a test is powerful. It means it has a high probability of rejecting the null when the null is false. And so that's measured by the power function over the alternative. And so we say a test is the most powerful test if its power function, its probability of rejecting, is higher than any other test when it properly should reject. So that's the definition. It doesn't say anything about the null hypothesis. It says only thing about the alternative. We can pictorially represent this thing. So here I have x and y axes, and let's say generically that my null hypothesis is this part of the space, and my alternative hypothesis, let's write it in red here. This part of my space is the alternative, just generically. And on my y-axis, I'm going to measure my power. Beta theta, and on my x-axis, of course, is theta. And my power function is the probability of rejecting the null hypothesis at my different values of theta. So when I'm in my when I'm in my null here, obviously I want that to be low. If the null is true, I want the probability of rejecting to be small. So I want my power function to be small. If I'm in my alternative, I want that power function to be large. I want to have a powerful test where I have a high probability of rejecting in this case, because if I'm in the alternative, the null is false, I really should reject. So there are many different power functions depending on the test. You might have a test that has a power function that looks like that, and maybe, so this is like, I don't know, beta 1, that's a power function of test. Maybe you have another test that looks like this. This is maybe beta 2. And what the uniformly most powerful test has is it's going to have a power function that's higher. So we'll call this beta star. The uniformly most powerful test, its power function is larger than all of the other power functions over the alternative. But I note that my definition only specifies it has to be larger over the alternative, right? Because that's where it should be correctly rejected. It doesn't actually say anything about what this power function should look like over the null. So there are many different possibilities. I could have a power function that looks like that. I could have it be higher in the null. I could have it be always lower, right? So there are many different possibilities here. And the definition is kind of agnostic. The power function would be higher, lower, the same, somewhere in between over the null. we don't care. That's not what our most powerful test. We say a test is powerful when it correctly rejects a lot. So we want this power function to be larger over the alternative. Ideally, obviously, you want the power function to be low. That's the probability of rejecting to be low when the null is true. But this definition is not going to specifically say anything about that. So that's our kind of pictorial definition of most powerful test. It just has a higher power function than every possible theta in the alternative. So we defined it in terms of some collection of tests, some C. And we didn't say what collection, right? Typically, and what we're going to look at, let's define the UMP level or size alpha test. So typically, we're going to consider our collection, our capital C, to be the set of all either level alpha test or size alpha test. So recall that a level alpha test has a maximum probability for rejecting over the null of well, let's go. So what's our size alpha test, right? So we define these in terms of both level and size. So if we go back, actually, we can go back to our definition here from lecture 20, right? So a size is that the maximum over the null is alpha, and the level is less than or equal to alpha. So let's go back. So a size alpha test, let's say a size alpha test, is that the maximum over our null of beta theta is alpha, and a level alpha test is that the maximum theta over our null of beta is not more than alpha, right? So typically we're going to look at collections of either all size alpha tests or all level alpha tests for a particular hypothesis. So the UMP level alpha test, or the UMP size alpha test, is the most powerful test among all. So let me write this down. The UMP, and let's go with size first. Size alpha test is the UMP, uniform most powerful test, among the collection of size alpha tests for a hypothesis. So if we consider, for a particular hypothesis, we consider all size alpha tests, that's a collection of tests, and we could talk about the most powerful test among all size alpha. Kind of similarly, the UMP level alpha test is the uniformly most powerful test among all level alpha tests of a particular hypothesis. So typically, well, you can define you could define a UMP test among a different class. There's things called unbiased tests, but we're not going to talk about too much. But for this course, we can talk about either size alpha or level alpha tests. So pictorially, again, if we go back to our little picture here, so here is the null, here is the alternative, right? Something like that. And we look at our power function over theta. If I set a level alpha test or a size alpha test, so typically we work with level alpha tests. If I look at a level alpha test, that basically says that the power function has to be below alpha over the null. So, for example, something with a power function that looks like this would be a level alpha test, because over the null hypothesis, the beta is lower than alpha. So the maximum probability of rejecting under the null, this is my function beta, is less than alpha, and that makes it a level alpha test by our definition here. And typically we want, obviously, beta to be higher in this part over the alternative because we want to reject more there. So typically you don't get something that looks like that. That would be a very bad test. That would say you have a high probability of rejecting when the null is true and not when the alternative is true. So if that is one particular level alpha test, you could have another level alpha test. Maybe it looks like this. This is some other level alpha test. And the UMP level alpha test would have, let's say, a beta star that is higher in the alternative. This is going to be a bad picture. Let's try it like this again. It's going to be higher in the alternative. But once we're in the null, it doesn't have to be necessarily higher. It doesn't necessarily have to be lower. So it could go something like that. That's still allowed. It's still a level alpha test because it has a power function that is below alpha over the null, and its power function is higher over the alternative. So that's what it means to be a most powerful test. And typically, we're going to talk about UMP level alpha or UMP size alpha tests. And we're going to talk today about how do we find these, and under what conditions can we be sure that the test we've developed is the best kind of level alpha test. So the idea behind this kind of hypothesis testing is I'm going to control my type 1 error by a threshold, let's call it alpha. So I'm going to force my power function to be below this, and then I'm going to try and maximize my power function over the alternative. So I want a very powerful test, so high over the alternative, but it has to be below a threshold on the null. So this is the typical way you could do this. The reason why we restrict ourselves to a class of tests is that there is generally no best test for the same overall, right? For the same reason there's no kind of best estimator. You want something that is best at all possible theta. And that's not generally possible unless you put some restrictions. And so one of the restrictions is if I restrict the size or the level of the test, say to be alpha, then in some cases I can get the best test. But if I don't restrict that, there's not generally going to be a best test. And so much like our UMBUEs, there we restricted things to be unbiased. And that allowed us to get a best estimator. If we restricted things to be unbiased, there is no estimator that is best at all possible values of theta. And the same thing, if we don't have a totally unrestricted test, there is no best test at all possible values of theta. If we put some restrictions, in this case we make it level alpha, for example, we control the type 1, then we can sometimes get an easy answer. So let's start to build this up. And to build up cases where we can show that something is best, we're going to consider again simple hypotheses. So a simple hypothesis is where I have one outcome, or one possible value of theta in my null, and one possible value of theta in my alternative. So The null is that theta is, let's say, little theta naught, and the alternative is that theta is little theta a, right? So one possible outcome. So my whole space, capital theta, is just theta naught and theta a. Capital theta naught, which is my space by null, my space of null hypotheses, is just this one little value. Let's call it generic little theta naught. And the possible space of the alternative hypothesis, capital theta a, is just has one outcome, little theta a. So maybe it's like null is 2, the alternative is 5, the null is 3, the alternative is 7, right? So you can pick different values. But a simple hypothesis is just one where there's only two outcomes. It's this or it's that, not like a interval of possibilities that we're testing. In this case, we can also consider the LRT, the likelihood ratio test. So LRT, right, looks at lambda, which we estimate theta naught at, and divide by theta hat, right? So we look at L of theta naught hat, divide by L of theta hat. And one way that you could write this is the arg max over theta in capital theta naught of L of theta over the MLE is the arg max, I'm sorry, not arg max, it's just maximum, isn't it? Yep, it's just maximum. Over the maximum of all possible thetas, L of theta. Now, if we go back to our definition here, capital theta naught just has one value. So the maximum value is just that one value, right? So our numerator is always L of theta naught, right? There's only one value in my null hypothesis. And the denominator could take on one of two values. It can either take on, so we're maximizing for the denominator, we're maximizing over the combined space of theta naught, little theta naught, or little theta a. So it could be the denominator is little theta naught, or it could be the denominator has little theta a. So we'll get two possibilities. It's either either denominator is again L of little theta naught, or the denominator is L of little theta a. So when is this going to happen? Right, so this first one's obviously 1. Well, the bottom is just going to pick whichever one is larger. So we're going to pick L. This will happen if L of theta naught is bigger than L of theta a. And this will happen in the reverse if L of theta naught is less than L of theta a. That's all it means to be a MLE, is we're going to pick, right? We're going to pick the one that's larger. So if L of theta naught is larger, we'll put it in the denominator. If L of theta a is larger, we'll put that in the denominator. And so my LRT, we can kind of succinctly write this out. My likelihood ratio test statistic is 1 if the null hypothesis point is more likely than the alternative. So L of theta naught is bigger than L of theta a. Or it's this ratio, L of theta naught over L of theta a, if the alternative is more likely. If L of theta a is bigger than L of theta naught, right? So those are my two cases. Recall that for my LRT, I reject my null hypothesis if lambda is small, below some threshold C. We determine a threshold. In reality, we determine the threshold so that we control our type 1 error. So for the LRT, I'm going to reject if lambda is less than or equal to some c. So when my c is between 0 and 1, I'm never going to reject in this case. Right? Because my lambda is just 1. And why would I reject? Because it says, it makes sense because the point in my null is more likely than the point in my alternative. So why would I reject if the point in my null is more likely than the point in my alternative? I wouldn't. So I'm not going to reject in that case. I will reject if L of theta naught, if L of theta A is larger than L of theta naught by enough. So let me write this out in words. Right, so 1, notice I'm not ever going to reject if the null hypothesis is more likely than the alternative, which makes sense. Null is more likely than the alternative. I will reject if L of theta A is sufficiently more likely than the alternative, than the null, right? So if the null is more likely, I'm never going to reject. If the alternative is sufficiently many more times likely than the null, I will reject the null. So when people talk about how the hypothesis testing protects the null, this is a case, right? If the null is more likely, end of story, not going to rejecting it, protecting it. If the alternative is more likely, it not just has to be more likely, it has to be some number of times more likely in order for me to reject. So I will reject if, and let me write it this way, right? So I'm going to reject if my ratio, L of theta naught over theta A, is less than or equal to C, i.e., and there's a couple different ways you can write this. Either I can move my L of theta A over, that is L of theta naught is C times less likely than L of theta A. So my null is C times less likely than my alternative. That's one way of thinking about it. Or you could flip this around if L of theta A is more than some number k, let's say, times as likely as L of theta naught. So here k is just 1 over c. So you'll see this written both ways. Some people in some texts write it the second way. I tend to write it the first way. It doesn't really matter. The point is that in our nice simple hypothesis, this actually comports with intuition, right? I only have 2 points, so let me just evaluate the likelihood for these 2 points. If the null hypothesis is more likely, not going to reject. If the alternative hypothesis is more than k times as likely as the null, I'll reject. Or alternatively, if the null hypothesis is less than c times as likely as the alternative, I will reject. So in this first simple hypothesis, which is the simplest place to start when trying to develop what the most powerful test is, our likelihood ratio test just boils down to evaluating the likelihood at my 2 points, the 1 point in the null, the 1 point in the alternative, seeing if the one in the alternative is many more times likely than the one in the null, and therefore I reject in that case. Okay. So what's the punchline here? I'll give you the punchline up front. Why am I talking about simple hypotheses? It's because there's a really nice theorem for simple hypotheses. So in words, for simple hypotheses, hypotheses, that's supposed to read that, the UMP level alpha test is the LRT. So this procedure of LRT for simple hypotheses is the UMP level alpha test. So among all tests testing this simple hypothesis, whose level, that is, whose maximum probability of making a type 1 error is less than or equal to alpha, the best test we can come up with, the most powerful test, the test that maximizes our probability of correctly rejecting, at every possible value of theta is the likelihood ratio test. So the reason we talked about that is that that's the best we can do. This is codified in a theorem, or written in a theorem, called the Neyman-Pearson theorem. But it's basically, I'm just going to rewrite what I said in words here. It's typically called, I guess, the Neyman-Pearson lemma. Why it's called lemma as opposed to theorem, I don't know. So Neyman-Pearson lemma is just going to recapitulate this whole discussion. Consider testing my null hypothesis. Theta is, let's say, theta naught, versus my alternative hypothesis. Theta is theta A, with a LRT lambda, first of all, that's not how you spell with a LRT, so that I reject H naught if lambda, which is going to be L of theta naught divided by L of theta A, is less than or equal to some constant C. And I can say where, parenthetically, where C is chosen so that the probability, right? So why don't you see that as a level alpha test? What does that mean? A level alpha test, so let me just write this real quick as a parenthetical up here. For a simple hypothesis where I only have one thing, right? If I have a level alpha test, that is the maximum probability over theta in my null of, let's say, of rejecting. In this case, that's the probability of rejecting is lambda is less than or equal to C for a LRT test. We want that to be less than or equal to alpha. Now, I'm maximizing that for my null. There is only one thing in my null, right? So this is the same thing as saying the probability under that one case in my null, when theta is theta naught, lambda less than or equal to C is less than or equal to alpha. So, and this is the same thing is true of a size alpha test, right? So if I were to change this to equal sign, this would be a size alpha test. All right. And the Neyman-Pearson specifically says something about a size alpha test. So we're testing this simple hypothesis, theta naught versus theta A. We're going to use this LRT, and we're going to choose C so that my type 1 error probability is alpha. So this is ensuring that our test is size alpha. And then what's the punchline? This is the UMP level, or surely size. And we can even say one thing further is the unique UMP size alpha test, or level alpha test. So you can rework this theorem with level or size, doesn't really matter. Let's just stick with size alpha test. So the whole theorem basically says if I have a simple hypothesis, I'm going to use my LRT, I'm going to choose the constant for my likelihood ratio test to ensure it's a size alpha test. And if I do this, this is going to be the uniformly most powerful size alpha test, and in fact it's a uniquely UMP size alpha test. Let me actually back up on that. I think that we should be a little careful because we might not always, if for discrete cases, it might not be unique. Let's just say it's the UMP size alpha test. Okay, that's definitely true. In some cases, this will be unique, although I don't think we can always definitely guarantee that this is going to be unique. For continuous cases, probably is. But if we have discrete cases, you might be able to get away with some tomfoolery there. Okay, so let's consider an example, maybe a couple examples. Example. So let's go back again to our example where our favorite normal example. So our data comes from a normal distribution with a mean theta. We don't know, but we know the variance, sigma squared. And we're going to consider testing a simple hypothesis, which is theta is some value a, versus the alternative, which is that theta is some other value b. Simple hypothesis. And we can test this using our likelihood ratio test. Using our LRT, so we let lambda, right? How do we want to write this? This is going to be, typically we write this as the null over the alternative, right? So we say it's L of A over L of B. So we need to look at this thing. Now, there's some algebra here, but one can show that this is going to be proportional to at least a exponential of n times a squared minus b squared plus, oh, sorry, that's backwards, b squared minus a squared plus 2 a minus b times n x bar divided by 2 sigma squared. So let's just say this is probably exactly, there's probably some constant out front, but it's at least proportional to that. So and I'll leave that as an exercise to you. You can show that, I mean, it's just the ratio of two normals, right? And you can kind of see that you'll get something along these lines. This looks something like what you get out of a normal. But that's what lambda is going to be. And so the LRT says reject if lambda is less than some value c. We're going to have to see how we choose that. So equivalently, if I take logs on both sides, or log of lambda is less than or equal to log of c, so that would say that that's equivalent to saying that n times b squared minus a squared plus 2a minus b and x bar less than or equal to, and I can move my 2 sigma over, let's say something like this. And a and b are fixed constants, so I could actually, and n are fixed constants, I could actually move this all over. This is going to say x bar is going to be, so I have to be a little bit careful here, because it's going to matter if I divide by a minus b, it's going to matter if a is bigger than b. Let's say b is bigger than a, right? If b is bigger than a, this thing's negative, so I have to flip my sign around when I divide through by that, right? So I basically, it'd be like 2 sigma squared log c. I can move this n b squared minus a squared over. So I can straight up subtract that, but then I'm going to divide through by 2a minus b times n, right? And there I have to be careful because a minus b in this case is negative, so I have to flip. So I had to flip this inequality sign. Okay. Now I don't particularly care about this constant. We could just call it C star. It doesn't really matter. The main idea is that my likelihood ratio test is going to reject if x bar is too large. So a gut check we should have is, does that make sense? So the hypothesis I'm testing is that, and this is why it matters if b is bigger than a or a is bigger than b. So I'm testing my null, which is its a, which is smaller, against the alternative, which is b is larger. And I'm testing a mean, right? Theta is our mean. So I'm trying to test, is my mean a or is it some larger value b? If I use my LRT, if you believe my algebra, and you do a little bit of rearranging, the LRT is equivalent to saying that x bar, that I'm going to reject if x bar is bigger than some threshold. Let's just call it generically C star. It doesn't really matter exactly what it is, because the C star is going to be determined by keeping my test size alpha. And that makes sense, because if my x bar is large enough, I'm going to think that actually the alternative to true them is my mean is the larger value b rather than the smaller value a. And if it's not large enough, I'm not going to reject. So it makes sense to reject if x bar is too large. So the LRT is doing something reasonable. And so you could have left it here and said it's whatever we take, log c unless or log lambda less than or equal to c, or lambda is less than or equal to c. You could have stopped at many places. You have to choose your c to ensure that it's size alpha in this case. Or you could just say it's going to reject when it's bigger than some constant, and implicitly we're choosing c. So how do we choose this thing? C star. We want, in our case, a size alpha test, right? So why do we want a size alpha test? Is because then we can apply our Neyman Pearson lemma, and we can guarantee that this test will be the most powerful. So how do we make this thing size alpha, right? Well, we can play tricks like we played last time, right? So this is equivalent to looking at x bar minus a over sigma over root n is bigger than, let's say, c star minus a over sigma over root n, right? And we want, so I just did, subtracted a and divided by sigma and root n on each side, so that's an equivalent test. I'm going to reject the same parts. Under the null hypothesis, which is where we calculate the size of a test. The size is the maximum probability of rejecting. This thing here is a standard normal, right? So if the true mean is a, theta is a, then x bar minus a over sigma over root n is standard normal. And so if I want, in our case, the size, the probability when theta is a, the maximum probability of the null, there's only one option under the null, which is when theta is a. I want the probability that x bar minus a over sigma over root n greater than or equal to c star minus a over sigma over root n. I want this to be equal to alpha, right? That is my size of my test, right? And I choose my C star, or alternatively, I choose my whole thing on the right. I want this whole thing to be what we're calling C of alpha, right? I just basically want to choose it as the point on a standard normal with alpha to the right of it. So this is my standard normal distribution. So what does that mean? So C star is equal to, well, I'll just solve back. It's a plus sigma over root n times z alpha. So what's my overall test? There's a couple ways of doing this. Alternatively, there's a couple ways. You've seen here how many different versions of this test you could write. They're all kind of equivalent. What I've written here is that we're going to reject is to reject when x bar is bigger than or equal to a plus sigma over root n z alpha, or equivalently, I could actually calculate x bar minus a over sigma over root n is bigger than z alpha. All right, and z alpha you get from a probability table. You look it up, you find it's like 1.64 or 1.9 something, right? It's just some threshold. So either of these are kind of equivalent versions of the test, and they both have kind of nice interpretations. Basically, I'm going to reject. I particularly like this first one because it's basically like I'm going to reject if x bar is bigger, not only bigger than a, but sufficiently bigger than a. It's z alpha times the standard error of x bar bigger than a. And because if I choose that C star in that way, this thing is a size alpha test, and by Neyman Pearson, it is the UMP size, not level, size alpha test. So we can sleep well at night knowing that this is kind of the best thing to do. So that's, much of this we did last time, so it's a nice little recap of that normal example. And in the simple hypothesis scenario, this is the best thing to do. So it says Neyman Pearson. Let's look at another example. This is maybe a bit simpler of an example. Let's assume we just have one data point, x, and it has some binomial distribution. And it's binomial 2 theta, and we don't know theta. So you could think of this as like flipping 2 coins with an unknown probability of heads, theta. So thetas are unknown probability of heads. And you can think of this kind of like flipping 2 coins and counting how many heads you get. All right, and so that's the data we collect, and we want to test the hypothesis. Maybe. I can tell you want to do this. The hypothesis we want to test is maybe the null is that 50-50, it's a fair coin. And we're working now with just simple hypotheses. So we only allowed one option alternative, and maybe the alternative is that it's 3/4. Yeah, maybe not the most realistic test, but you build up from Neyman Pearson. We'll get to the more interesting and complicated problem of composite hypotheses, where we have more than 2 options. But let's say we wanted to test the hypothesis that the unknown probability is 1/2 versus the unknown probability was 3/4. Right? And we're going to do this using an LRT. And so lambda for our simple hypothesis of an LRT is simply L of 1/2 over L of 3/4. And we're going to reject if lambda is too small. And Cool. This is a simple enough case. This is not a continuous case, so we had the normal example. It's actually a simple enough case. We can actually enumerate all the possible values of lambda, right? So x can take on 3 values. And what are our 3 possible values? 0, 1, or 2. It's a binomial 2 theta. What can lambda take on? Well, let's just make a little table. Here's what x can take on. Has 3 possible values. 0, 1, or 2. And let's look at lambda. Sorry, this is not. No, this is good, right? Okay, we can look at what lambda is. And we can kind of fill in this whole table, right? So this first value here, right, is going to be lambda when x is 0. So let's say lambda of 0, right? And that is the likelihood function when x, right? So the likelihood function, of course, is just f of x. Well, the likelihood function 1/2 of f of x at 1/2. And likelihood function of 3/4 is f of x when theta is 3/4, right? So this is basically the probability that x is 0, let's say when theta is 1/2, divided by the probability when theta is 3/4 of x being 0, right? So that would be my first value here. And you can think about why that's the correct likelihood. Right, this is for the discrete case, the likelihood is just the, right? In all cases, the likelihood is just the joint distribution. In the discrete case, it's just the joint PMF. And so the PMF is just the probability, right, in our discrete case. And so that would be our LRT statistic at 0, when x is 0. And you could calculate this. It's going to be something like the top is 2, choose 0, then it's 1/2 to the 0, 1/2 to the 2, and then divided by, so these are just using the binomial PDF or PMF formula. Bottom is 3/4, so 2, choose 0, 3/4 to the 0, and 1/4 to the 2. And this is going to give us what? I think 4 if we do that. So it's 1/16 on the bottom and 1/4 on the top. So that should give us 4 overall. So our value here is 4. And you can calculate the other values. And I'm not going to make you calculate them. So it's 4, 4/3, and 4/9. Notice these are not probabilities. Lambda is not probability. It's a ratio of 2 probabilities, so that can take on any number, any positive number. So it doesn't have to be between 0 and 1 or anything like that. But you can calculate those values, and that's what those values are. 4, 4/3, 4/9. And the LRT says, right, as we said here, the LRT says we're going to reject if lambda is smaller than some threshold. So here are our possible values of lambda here. It could take on 4/9, which is the smallest one. The next one is 4/3, that's slightly larger, and then 4 is somewhere over here, right? And what we need to do is we choose our value of c. So maybe I choose my c there, and I'm going to reject, or maybe I choose my c there, or I'm going to reject. Notice that it doesn't really matter if I choose c here or I choose c there, because we're going to reject in the same places, right? So this is x is equal to 2, this is x is equal to 1, this is x is equal to 0, right? And depending on where I set my threshold, right? For example, if x is 0, so I flip 2 coins and I get both tails, do I think my probability, my theta is 1/2 or 3/4? Probably more likely to be 1/2. Maybe. What if I get 1 head? 1/2 or 3/4? Well, it depends on what I'm going to set my threshold at for my LRT? What if we get both of my tosses are heads? Is it more likely it's that the probability is 1/2 or 3/4? Depends on where I set my threshold. Probably in that case, you would probably say it's more likely to be 3/4. So there's gonna be some choice here. Maybe I set my value C here. So if I choose any C, where C is between 4/9 and 4/3, right? So these are my values at lambda. I'm basically only going to reject only when x is 2. Then my size, which is my probability of type 1 error, the max probability of type 1 error, there's only one thing in my null, so this is probability when theta is 1/2. And let's say lambda less than C. And if I put my C here, then this is the probability when theta is 1/2 that x is 2, right? Because I'm only going to see a lambda less than whatever that C value is when x is 2. So that's when I'm going to reject. My rejection region is exactly x is equal to 2. Right? So it's almost so simple a problem, it's confusing, right? Turns out this probability you can show is 1/4. And so this test by the Neyman-Pearson lemma is the UMP size alpha is 1/4 test. So there's a kind of discrete example. It's almost maybe the first one to start with. It's very simple. But if I wanted to test this hypothesis of I'm going to flip 2 coins and I want to test this really simple hypothesis of the probability is 1/2 or the probability is 3/4, which should I favor? The UMP, if I want to control my type 1 error to be 1/4, then the UMP alpha test would be to do the LRT and set my C at any value between 4/9 and 4/3. If I were to move my C to somewhere in this place, I would have the UMP wouldn't be alpha as 1/4 now, but it'd be the UMP for whatever size test that is. In that case, it's probably like 3/4 or something like that, right? Yeah, indeed, that's probably what it would be. So that's a kind of nice example. We've done these normal examples several times. That's a different kind of flavor example of a discrete test. Okay, so let's build up, and we're not going to finish this today, but we're going to build up to next time talking about non-simple hypotheses, because a hypothesis like this where I'm testing something really simple like 1/2 versus 3/4 is not the most realistic hypothesis, right? We typically test, something less than this or bigger than this, is it equal to this or not equal to this, right? And so that's kind of the more realistic, interesting, and it turns out that can be hard. In some cases, we'll be able to find the most powerful test, not always though. So we're going to try and build up our theory to that. Before moving on, it's worth noting that, and this would be a nice little fact that everyone should appreciate, is that one can show that the likelihood ratio test is ultimately just a function of a sufficient statistic. So here in our binomial example, we had one data point, so x was a sufficient statistic for theta, and x showed up in our test. If we go back up to our normal example, our test ultimately, for example here, involved x bar. X bar is a sufficient statistic, and so it turns out that the LRT is, in this case, a function of a sufficient statistic. You can phrase the test as a test as a thresholding of a sufficient statistic. And that is always true, is that every LRT, every likelihood ratio test, is a function of some sufficient statistic. So let's just write that down as a theorem. So the fact that these tests are interpretable is not a mistake. They're interpretable because you're using basically sufficient statistics, which are usually pretty interpretable. And that's just a general fact of LRTs. So let's say the theorem is LRTs are a function of a sufficient statistic. That's kind of the theorem title. I'm not going to go through a whole long proof of that, but basically, right, so our LRT, our likelihood ratio test statistic, is ultimately a function of x, right? So I kind of suppressed the x, but it's a statistic. It's just a function of x, like the other one, the normal test, it was like x bar or something like that, right? Or some monotonic function of x bar. But ultimately, the general form is L of theta naught hat over L of theta hat, where theta hat is the MLE and theta naught hat is the MLE restricted to the null hypothesis. And the theorem basically says that you can write this as some other function, lambda star of t, where lambda star is some function that doesn't involve x, and a sufficient statistic. So, as you've noticed now, when you're using likelihoods, sufficient statistics come up everywhere. They kind of, likelihoods are very powerful concepts, and sufficient statistics kind of nicely summarize likelihoods or capture the information in a likelihood function. So you can always write these things as some other function of a sufficient statistic. What it is might depend. The proof is I'll just sketch the proof. It's pretty much the whole proof. Is that, recall that MLEs, theta naught hat and theta hat, are functions of sufficient statistics. So we argued before, at least we claimed, that MLEs are functions of sufficient statistics, and okay, and then, you know, the likelihood ratio test statistic lambda is a function of MLEs, therefore kind of transitively the likelihood ratio test statistic, is a function of the sufficient statistics also. So that's kind of the sketch of the proof. It's a bit of an aside, although we'll come back because we can basically, instead of, the reason this is a useful theorem is instead of phrasing all of these things in terms of a likelihood ratio test statistic lambda, which sometimes is not so interpretable, we can phrase all of these tests in terms of a sufficient statistic, which is often more interpretable. And that will be the case for these composite hypotheses. So the last couple of minutes here, I want to just talk about, we're going to talk about a property of likelihoods. And it's going to seem like an obscure property, but it's going to be used. It's unfortunately necessary. So unfortunately, for simple hypotheses, A versus B, right, it's very easy to say what the UMP level alpha test is. For composite hypotheses, where we have multiple outcomes in a null and multiple thetas in the alternative, right, it's actually not quite as simple, and you need some more conditions. And generally, it's harder to get a best test in these cases. One of the things that we're going to need is called the monotone likelihood ratio property. So let's just define that. And this is typically denoted MLR for monotone likelihood ratio. So we say a family of PDFs has the MLR property. So family of PDFs, and generically this family of PDFs is F theta. So it's a collection of PDFs indexed by some parameter theta. We say this family of PDFs has the MLR property if I look at F, let's call it theta 2 of x, divided by F theta 1 of x. So so theta 2 is going to be bigger than theta 1. So what I'm going to do is I'm going to pick some, right? So this family of PDFs is indexed by some parameter theta, and I'm going to pick some parameter theta 1 and theta 2 where theta 2 is larger. And I'm going to look at the ratio, the likelihood ratio, hence the name, of F theta 2 over F theta 1. So one way to think about this is like lambda L of theta 2 over L of theta 1, right? This is basically the likelihood ratio, right? Because PDFs are just a rebranding of likelihoods, or likelihoods are a rebranding of PDFs. So if I look at this ratio, this likelihood ratio, this thing has the MLR property if this likelihood ratio is monotone, is non-decreasing as a function of x. So let's just go back over this. I have a set of PDFs. We say this collection of PDFs has the monotone likelihood ratio property. If I look at the likelihood ratio, L of theta 2 over L of theta 1, where theta 2 is bigger than theta 1, but fixed, if I look at this as a function of x, this thing should be non-decreasing as a function of x. In that case, they say it has a monotone likelihood ratio property. So if I fix any two thetas, theta 2 and theta 1, look at the larger theta L of theta over L of the smaller theta, and that thing you could think about as a function of x. If that thing is non-decreasing, we say this thing has the MLR property. So this seems like a kind of obscure property. It's a little bit obscure. You can see how it's related to ultimately the likelihood ratio test, because it's the ratio of two likelihoods. But it's going to ensure that we're going to be able to, it's kind of a technical condition, unfortunately, that's going to be necessary to ensure that we can find a best test. So yeah, so that's this is the MLR property, which is something you have to learn to appreciate, even though it is a bit abstract. Nicely enough, there is, maybe not surprisingly, a nice theorem that says for exponential families, this is not so bad. If my collection of PDFs is an exponential family, so that F theta of x is, how do we do this? C of theta, h of x, exp to the w of theta times x. So something like this. So if I write it like this, notice I have not t of x, but x here. Then if w of theta is non-decreasing in theta, this family has the MLR property. So if I can show that my family is an exponential, and I can show that you can write it as some w with some w theta up in my exponent of my exponential family times x, one can show that this thing has the MLR property if w is increasing. So that's actually a much easier condition to check generally. We just check its exponential family. We check that this w of theta is increasing. So the proof of this is actually not too bad, right? We want to look at L of theta 2 over L of theta 1, which is C of theta 2 h of x exp to the w of theta 2 times x divided by C of theta 1 h of x, something like this, all right? And we know that theta 2 is bigger than theta 1. We don't really care about the C of theta 2 over C of theta 1. This thing is basically proportional. First of all, this h's cancel. But we could basically say this is proportional to w of theta 2 minus w of theta 1 times x, right? Ignore the constants out front. And if w is non-decreasing, then this thing is positive. Because theta 2 is bigger than theta 1, it means, so w non-decreasing means, definitionally, that if theta 2 is bigger than theta 1, then w of theta 2 is at least w of theta 1, right? So this thing is at least non-negative, right? And so this thing basically looks like e to the some constant, some positive constant, let's say a times x, and this is increasing in x. So it has the MLR property. It's an increasing function of x for some, because it basically looks like e to the ax for some positive a, and so that thing is increasing in x. And so for exponential families, it's very easy to show they have the MLR property. So you write it in this form, and you check that that w has the right form. So we're going to stop there for today. This MLR property will be used next time to derive our kind of theorem about most powerful tests when we have composite hypotheses, when more complicated hypotheses than just some simple hypotheses. But we're gonna call it there for now.